Hello, this is Mrs. Butcher. This video is the second one on exponential growth and decay. Yesterday we talked about how the exponential standard form is going to be y equals, and then you could have positive or negative, and then a number a, times a number b raised to the x. We could have a horizontal shift, and we could have a vertical shift. So that's the standard form. Today we're going to talk about how this applies to application problems, real-world problems. And first we'll start with exponential growth models. An exponential growth model looks like y equals, and then you have an a value. And then we're going to put 1 plus r in parentheses as your number raised to the, and then we're going to use a t instead of xt power. So y is going to be your amount that you're trying to find, and a is going to be the initial amount that you had. R is going to be your rate, or your rate of growth, so it will be a percentage in decimal form, and t stands for the time. And then when we're talking about these, the 1 plus r value is often called your growth factor. So if r was 50%, it was growing at a rate of 50% per year, then r would be 0.5, so your growth factor would be 1.5. And that's because the 1 is in there to account for the original amount you already had, plus the new amount with the growth. Alright, so I'm going to call this example 6 because we're continuing on past the examples we've already done. In 1997, 0.42 million DVD players were sold. The sales increased at a rate of 147% per year. How many were sold in 2002? So we're going to just take these numbers, put them into our exponential growth model. We know it's growth because it says increase. Ooh. Right there, increase. So we know we're going to use the growth model, which is y equals a 1 plus r raised to the t. Y is how many were sold in 2002. That's what we want to know. A is going to be, in 1997, 0.42 million. So we'll just use 0.42 and then let our answer be in millions. 1 plus, and then the rate is 147%, so that's 1.47. That's a very huge increase. Raised to the t power. And so between 97 and 2002, 5 years went by. So that means we're going to raise it to the 5th power. So now we have to do, remember we have to do what's in here first. We get 2.47. We raise it to the 5th power. And then we multiply that by 0.42. Remember your PEMDAS, and you should get an answer of 38.613, and I always want 3 decimal places. And remember, we let this be 0.42, so we said it was in millions. So this is also in millions. Million DVD players. Make sure you get your units right. All right, now that's for things that grow exponentially, like, sales increasing or population growth or things like that. We also have exponential decay models for things that decay, that get smaller over time. And that is just going to be y equals a 1 minus r to the t. It's exactly the same as growth, only we're subtracting our rate instead of adding it. So y is still our final amount, a is still our initial amount, r is still our rate, and t is still time. It's just that if I was decaying at a rate of 50%, per year, whatever the time is, then I would want to multiply by 1 minus 0.5. So I would want 50% of what I had before. I don't want to account for what I had before and add that onto it because I'm taking away from it. All right, so now example 7. A new car costs $25,000. The value of the car decreases by 15% each year. Write a model giving the car's value after t years. All right, so this $25,000 is your initial amount, A. The value of the car decreases by 15% each year. That's your rate, R. and it's going to be 0.15. And we want to know, we just want to write the model. A model is the same thing as saying write the equation. So we want to say y equals, and then our initial amount, 25,000, 1 minus the rate raised to the t power. So we're writing the equation. And you can go ahead and leave it like this. You don't have to change this to 0.85 because this shows that 0.15 is your rate of decreasing. So now, what if I asked you, find the value of the car after 4 years? So now we're going to plug in a 4 for t. Just make sure that your units years match the units in the problem years, because if this said decreases by 15% each month, then we would need t to be in months. But in this case, it's years and years, so we're good. We're going to plug in a 4 for t. We're just going to do 25,000 times 1 minus 0.15, which is 0.85, raised to the 4th power. So first you're going to take 0.85, raise it to the 4th power, and then multiply that answer by 25,000. Okay? Or if you plug it all in the calculator in one line, it'll work. But don't multiply by 25,000 before you raise it to the 4th power, because 25,000 is not touching the 4th power. And when you do that, you will get an answer of $13,050.16. All right, another equation that has to do with exponential growth and decay, that's something we actually use in the real world a lot, is compound interest. And this is an equation I am making you memorize. So that equation is A equals P, big parenthesis, 1 plus R over N raised to the NT power, where A is your after amount, and P is your prior amount, your starting amount. P actually stands for principal, but if you think prior and after, then it's easy to keep them separated. The R is your rate. The N is going to be the number of times that is compounded per year. And that per year does matter. It's always going to be in years here. So this T is our time, and since we're compounding it per year, it is always years for these problems. So you'll just convert it to years if it's not. All right, let's do an example. All right, so you deposit $200 into an account that pays 3% monthly interest. How much do you have in 2 years? All right, so we've got our equation, A equals P, 1 plus R over N to the NT, which we've got memorized. Our after amount, that's what we want to know. How much will we have in 2 years? So I don't know yet. Our prior amount is the $200 that we started with. 1 plus, the rate is 3%, so 0.03, over N. Now N is how many times it's compounded per year, and it says monthly. So yeah, you got to know there's 12 months in a year, and it's going to be 12. If they compound it monthly, then after a year they will have compounded it 12 times. Raised to the 12 times, and then we want 2 years. So that means we're raising it to the 24th power because they're going to compound it a total of 24 times. All right, now you can plug this in your calculator. Just make sure you're careful with your parentheses, and you're going to get a nice answer of $212.35. 3% is not a lot of interest, but, for just putting your money into an account and letting it sit there for the bank holding it, $12 profit for doing absolutely nothing. That's okay, right? And when you have a lot more money than that, and when you find better interest rates than that, that's when you start earning good interest on your money. The last real-world equation we're going to deal with here is half-life. And yes, you have to have all of these memorized, including this one. Half-life is a science thing. You guys have heard of that, like when you've got something that decays, it decays half of its life, and then another half of its life, and then another half. So it's getting closer and closer to zero, but never actually touching it. And the half-life would be the amount of time that it takes that thing, whatever it is, to decay by half. So here's your equation. A equals A sub 0 times 1/2 raised to the T over H. Okay? And another way we could write that equation, if you'd prefer, is A sub 0, and then instead of a half, we could have a 2, and then remember the reciprocal is a negative power, so we'd have negative T over H. I find the first one is much easier to memorize, but if you like the second one, go for it. Where A is your after amount, and A sub 0 would be your initial amount. T is your time, and H is your half-life. And just make sure that the units in your time and your half-life match. So if it's a half-life of 2 days, you want your time to be in days. If it was a half-life of 5,000 years, you'd want your time to be in years. All right, so in class, you're going to get a worksheet full of half-life problems. Well, all sorts of exponential growth and decay problems, but with some half-life problems. And this is the first one on that worksheet. So when you get to it, you can rewrite it or skip it, whatever. Arsenic 74 is used to locate brain tumors. It has a half-life of 17.5 days. Write the exponential decay function of a 90 milligram sample. Use the function to find the amount remaining after 6 days. So if you remember your equation, it's A equals A sub 0, 1/2 to the T over H. So my initial amount is 90 milligrams times 1/2 to the, and the time is 6 days, and the half-life is 17.5 days. So you can just pop that in your calculator, and you should get an answer of 70.96 milligrams. Come on, you know you think it's funny.